So, my dear students, today we will solve the numerical regarding Feynman diagrams. But before that, we should have a close look on the concepts lying behind this concept. Okay. So, let us start the revision process for Feynman diagram topic. Okay, with the different type of ultimate interactions or the forces that are present in our nature. Okay. So, by going from a strongest magnitude to weakest one, the strong nuclear force comes in the first place. Okay. And this is the force which is very responsible for binding together all the nucleons inside the nuclear environment. Okay. And then, if you will move to the second order, then the second force comes, that is your electromagnetic force, which is present in between any two charged particles. Okay. And then the third force is called your weak force, which is generally considered as the beta minus and beta plus type of radioactive decays. Okay. And here the given example of reaction, okay, this it belongs to your beta minus decay. And then the fourth one, which is called gravitational force, which is the weakest among all these forces. Okay? And we know that this force can be observed in between any two particles which contains mass within them. Okay? So these are the ultimate forces that we generally observe in our nature. Okay? Now, as I said you, that all these forces can also be called as your interactions. Okay? Because in our particle physics, we generally coin this term interaction very frequently. Okay? That means interaction is there. That means two or more particles are present in each of these cases. Yes. And if two and more particles are present, that means one mediator is also there who carries the force or the interaction from particle 1 to particle 2. Okay. And that mediator has a specific name and role for each of these reactions. Okay. And the name of all these your intermediate particles are exchange particles. Okay, which exchanges the force of the interaction between the two particles. Okay. And as each of these forces have different names, time delays, and also different features, so that's why we have categorized different fixed exchange particles for each of these cases. For example, gluon is the exchange particle for the strong nuclear force, whereas photon serves as the mediator particle for electromagnetic force. Okay. In the other hand, on the other hand, W plus, W minus, G0 are the exchange particles for beta plus, beta minus type of weak reactions, and graviton serves as the exchange particle for the weak force, gravitational force. Okay. Now the main task is, okay, generally which we face during the IB board examinations, okay, are we have to analyze all these interactions. Okay. So how can we do that? We have two ways to analyze all these interactions. Okay. One is just by writing the equations. For example, for beta minus decay, the conversion is neutron to proton and electron and antineutrino. Whereas there is another process through which we can visualize these equations. Okay. And that is the core concept of this video. Okay. That is Feynman diagram. So basically, we can say that Feynman diagrams are the diagrammatic representations of all these interactions in space and time. Yes, in space and time. Okay. Now, without going much detail into this concept, let us let us understand these Feynman diagrams via some of the important examples. Okay. And yes, let me remind you that you have to follow certain rules before drawing the Feynman diagrams for different tractions. Okay. So, for example, here, uh, as the equation may contain some of the particles and antiparticles, that means we have to represent the particle and antiparticle by some curves or arrows or shapes in the Feynman diagrams. So here the rule says you that the particles should be represented by means of your direct arrow. Okay. And the antiparticle can be represented by just a backward arrow. That's simple. Okay. And also for exchange particle, we have different lines to represent them in the Feynman diagram. Okay. So gluons means the exchange particle for your strong force. Okay. These are represented by these spiral or helical lines, whereas photons, the mediator particle, the exchange particle for your EM force, are represented by this zigzag line. Okay. W plus, W minus, G0. Okay. Which kind of exchange particle are these? Like weak. Okay. So, and these are represented by dotted or dashed lines. Okay. Now let us understand this. these rules, let us apply and understand to some of the basic representations. Okay. For example, this first line, okay, represents a particle moving in time only because its space, its position is fixed in the space. Okay. What does this line represent? The second line? The second line gives you the significance of a particle which moves from one place to another place in space, but the time here is constant for this line. That means this is an instantaneous process. It happens very quickly. Yeah. So for any kind of interactions, okay, if you want to draw the Feynman diagram, then we have to use this arrow, and this arrow represents, okay, the movement of a particle in both space and time. Okay. Both x and t coordinates are just changing continuously. Okay. Now let us apply all these rules to solve some of the important problems. Okay. The first common type of problem is your, or interaction you can say, is your beta minus decay. Okay, so whenever you come across these kind of Feynman diagram reactions or the interactions, okay, at first you have to identify which reaction is this. Okay. We means we have only 4 reactions or interactions with us in our nature. So which kind of interaction is this? So here this is your beta minus decay, where neutron is converted into proton. This is the main process, and along with this, okay, or during this reaction or interaction, we have one or two exchange particles there. So what is the exchange particle for your weak decay? That is your W minus, because it is weak. Now this W minus gives you the rest 2 particles. Okay. Now let us draw this. How to draw? At first we have to identify the reaction point or the interaction point. This arrow represents the interaction point. So by taking time along horizontal axis, okay, visualize the interaction line. Okay, you don't have to draw this, you only have to visualize. Okay, and in the reactant side we have neutron, the incoming neutron, like this, and on the product side we have proton, like this. Okay, and just at the interaction vertex, okay, you have to draw the exchange particle W minus, and this later on is converted into 2 more particles. Okay, one is your antiparticle, that is your antineutrino, and another one is your simple electron. Okay, so this is so simple. This is the way how to draw the Feynman diagram for beta decay. Okay. Now the same diagram can also be drawn by taking time along the vertical axis. Okay, let us do. Yeah. So here at first you have to visualize the interaction axis. Okay, and incoming particle is your neutron. This is neutron, and it gets converted into proton by exchanging W minus, and later on this W minus gives you 1 electron and 1 positron, not positron, sorry, that's my mistake, my bad. That's your antineutrino. Yeah. Okay, so this is one kind of problem that generally we face in IB exams. Okay, but the same equation can also be asked in the IB examination, but here the Feynman diagram should contain the quark contents of these neutron and proton. Okay, that's another kind of question you can get from the same equation. Okay, so you have to be prepared for that. Okay, so neutron, as we all know, that all the nucleons like neutron and proton consists of quarks. Okay, and quarks have different combinations and charges also. So let us at first find out the quark combination for neutron and proton. Okay, and this is given in your data booklet. You can use data booklet in your examination to find out the quark content of neutron and proton. Okay, here neutron has the combination like U, D, D. Okay, U has the charge plus 2 by 3 and D has the charge minus 1 by 3. Ultimately, whenever you will add all the charges, you will get the charge as 0, as neutron has 0 charge. Okay, the same goes for P, and the structure for P is a D, U, U. Okay, now what happens in the conversion from neutron to proton in terms of quarks? Okay, let me at first rearrange all these quark combinations like this: U, D, D, and this one U, D, U. So U remains the same, D also remains the same, but the second D gets converted into U. Okay, so here you can expect the exchange particle. Okay, Both these terms, these quarks remain the same throughout the interactions, but only one pair of quarks are involved in these kind of interactions. Okay, so let us write these quark combinations in order to represent the Feynman diagram. Okay, now yes, so this is another kind of question where you have to draw the Feynman diagram for beta decay. Okay, but in terms of quarks. So along time, taking time along your horizontal axis, you have to assume, you have to visualize the interaction line that is here, and then the incoming particle is your neutron. Okay, so neutron means what's the content for neutron, quark content for neutron? That's U, D and D. Okay, and what's the quark content for your proton? That's U, D and U. Okay, so these bottom two quarks remains the same, okay, during the conversion process, but the top particles are getting converted by giving W minus, okay, which later on gives you electron and antineutrino combination. Okay. The same thing can also be drawn by taking time along vertical axis. Okay, so vertical axis means you have to identify the vertex line, interaction line, and then so this is the reactant side. In the reactant side we have neutron. Neutron means what is the combination for neutron? Obviously this is U, D and D. Okay, now U remains the same, D also remains the same, but this D is converted into U. Okay, so by giving the exchange particle W minus, which later on gives you electron and antineutrino. Okay, so in this way you have to draw. Now let us take one more example. Yeah, so you all have to draw these lines. Okay, you have to represent the Feynman diagrams for this. The first case is electron absorbing gamma, means the photon. Okay, so electron is on the reactant side. At first visualize, don't draw this on the diagram. Okay, you only have to visualize this interaction axis or interaction line. Okay, so the incoming particle is electron, also one photon ray is coming, so the electron absorbs this photon and once again moves forward in space and time. Okay, so this is the process. Now if we want to show electron emitting gamma, okay, what will be the reaction here? Electron is coming. Okay, suppose this is your interaction axis, so electron is coming and it emits one gamma ray, and once again the electron goes or moves forward in the time. Okay, now moving to second kind of case, that is about your positron. If suppose positron is absorbing the gamma ray, then what will be the resultant Feynman diagram? Okay, same thing will happen, but for the arrow will be inverted. Okay, and gamma ray is coming here and once again it will move forward in space and time. Okay, and for this positron emitting gamma ray, that means suppose this is your interaction ray, so this is your positron. Okay, and it emits one gamma ray, once again it moves forward in time. Okay, why I'm indicating these backward lines, because these positrons are antiparticles. Okay, now three most important thing. First one I have done for you, that is pair production, in which one of the gamma ray, okay, gives the pair of positron particle and antiparticle. So this is the reaction. Okay, and now second task is for you, how to draw annihilation. You can just pause the video, draw it. Okay, I'm drawing it here. So one electron and positron pair is present in the reactant side. Okay, suppose this is your electron. Okay, and this is your interaction point. Yeah, and positron is also upcoming like this, and in the product side you will only get one gamma, and this is called annihilation, complete disappearance of all the incoming particles. Okay, and now the last important interaction is your electron-electron repulsion, which we have studied in our electrostatic chapter, but now here you have to represent this interaction in Feynman diagram. Okay, how to do that? Okay. Suppose time is taken along your this axis, horizontal axis. So how to do that? electron repulsion means these two particles are present in reactant side. So at first visualize the interaction line, and reactant side is this one, is the reactant side. So one electron is incoming, another electron is also incoming, okay, like this, okay. And just at the interaction vertex or interaction line, okay, suppose this first electron gives or exchanges, okay, one gamma ray. Why? Because this is electromagnetic force case. So gamma ray is the exchange particle. So this exchanges one gamma ray with the second electron and it moves away. And after taking this gamma ray, the second electron also moves away from the first one. So this is called repulsion, electrostatic repulsion in terms of Feynman diagrams. Okay. So here the same thing can also be represented in this diagram, second diagram, that is time along the horizontal axis. So this is the vertical or the interaction axis. Okay. Here this is the reactant side. So in the reactant side we have the two electrons just moving forward in space and time towards each other, and one of them exchanges the gamma ray, okay, gamma ray like this, and then they gets they have to undergo the repulsion there, okay. So this is electron, this is electron, okay. This is one electron, this is another electron. This is the way to represent the electrostatic repulsion in Feynman diagram, okay. Now we'll solve some of the previous year question regarding your Feynman diagrams, okay, and how this chapter is very much important for the 2024 batch, the last batch for IB examination with old syllabus, okay. So we'll analyze all these questions.